Bismillahirrahmanirrahim. Welcome to week 4 and 5 video lectures for basic engineering mechanics. In these 2 weeks we would be covering chapter number 3 of our book, which is about equilibrium of a particle. So let's start. So the basic concept in chapter number 3 is that we would find the conditions that are required for a single particle to be in equilibrium. We would learn how to draw a free body diagram, and we would solve for equilibrium of a particle in 2 dimensions and later in 3 dimensions. So the condition for equilibrium of a single particle is just that the sum of all the forces on that particle has to be equal to 0. So this is the only condition for a particle. For a rigid body we need other conditions also, which we would study in after a few lectures, but for a single particle we only need the sum of all the forces to be equal to 0, and it is a necessary and a sufficient condition. What does that mean? That if the sum of all the forces is equal to 0, we would have equilibrium, and on the other hand, if we have equilibrium, then that implies that sum of all the forces are equal to 0. This is what we call an if and only if condition. So to apply this equilibrium condition, we draw a free body diagram. A free body diagram is a diagram which accounts for all the forces acting on any body. If we draw all the forces acting on any body, that is what we call a free body diagram. So for example, we have this box here. If we want to draw its free body diagram, we would draw all 3 forces acting on it. So let's assume that there is a force which is due to gravity, there is a normal force due to the surface, and there is a frictional force which is F3. If we draw all 3 forces, we name them, that is a free body diagram of that body. We have to note that whenever we are drawing a free body diagram, sometimes there would be springs in our free body diagram. So we have to note that springs do not have a fixed length. They can expand or they can contract, which means that we have to use the formula F is equal to Ks, where F is the force applied on the spring and S is the extension and K is the spring constant. This is the basic Hooke's law that you might have studied in your intermediate. So let's look at a simple example. So the example that we are going to look at is for a spring. So we look at a very simple spring. So we have a spring connected to a ceiling and which has a 5 kg load connected to it. Okay. So now we know, so let's assume that we are also given a few things about the spring. First of all, the value of K, which is the spring constant for the spring, is 100 newtons per meter. Okay. This basically just means that if we apply a force of 100 newtons, the extension in the spring would be equal to 1 meters. The initial length of the spring is 2 meters, and we want to find L0. Initial length is L0, and we want to find L, which is the actual length in this configuration. Okay. So first of all, we know that just by looking at this diagram, that if we were to draw a free body diagram of this 5 kilogram mass, we know that the downward force is gravity, the upward force should be equal to downward force. So that means that there is a force of 50 newtons on the spring. So we know that for a spring, let's just change some color. Okay. So we know that force equals Ks, and so which means that S is just equal to the force divided by K. and the force is equal to 50 newtons, which is just mass times the gravity, and the K value is 100 Newton per meter, which means that S is nothing but 0.5 meters. So the extension is 0.5 meters, which implies that L is equal to L naught plus S, which means that L is equal to 2.5 meters. So the only purpose of this example is just to refresh your memory about springs and this formula F is equal to Ks. So let's move on. So now another thing we have very frequently in our free body diagrams is cables and pulleys. Anytime we have cables, we would assume that these cables are ideal, which means that they have zero mass and they have no elasticity. So their length is fixed and they have no mass. So which means that they have no inertia. What does that mean? That implies that the tension in the cable and the string is constant, which means that if we are pulling the string with a tension T on this end, the same tension would be transmitted to every portion of the string. Okay, and why is that so? Because the string has zero mass. So if it has any non-zero force on it, just by using F is equal to ma, we would have infinite acceleration. Okay, so when we assume that the mass is zero, it automatically implies that the tension in the spring should be constant. The second assumption we are going to use is that of an ideal pulley, which basically means that all the pulleys in our system, they have zero mass and they have no friction. So it does not take any force to rotate the pulley just by itself. So these are the assumptions that we are going to use for many problems and free body diagrams in this course. Okay, so another assumption is that of a smooth contact. A smooth contact is a contact which is frictionless. So anytime we say a smooth contact, we mean that there is no friction, but there is a normal force. So for example, we have this mass which is placed on this tilted surface. So because of this mass, there would be a normal force which would be perpendicular to this surface, but there would be no frictional force. So if we are looking at this diagram, we can draw the free body diagram which would look something like this. Okay. So another thing we have already used it many times is just to reiterate that gravity is just a downward force which is equal to mass times the gravitational acceleration, and we would use its value to be 10 meter per second squared. So what is the procedure of drawing a free body diagram? So first of all, we draw the outline shape. That means that we isolate whatever the shape is from the rest of the environment. We just draw, for example, if we are trying to draw the free body diagram of a block, we would just draw the outline of the block and we would not draw anything else which is connected to that block. The second thing we would do is that we would show all the forces acting on that block, and the forces can either be active or reactive. What does that mean? An active force is a force which produces motion, and a reactive force is a force which stops motion. So for example, gravity is an active force. It tries to produce motion, but normal force is a reactive force. It tries to stop motion. The next step we do is that we identify each force. So let's assume that our block has 4 forces on it. So there would be some forces which are known, and there would of course be some forces which would be unknown. So we write the value of all the known forces and we label all the unknown forces to make geometric equations. So these are the 3 steps. When we follow these 3 steps, we have ourselves a free body diagram. Okay. Another important point to make here is that if any time we have a rigid body is something which is not a particle, which has some volume, while a particle has no volume. So anytime we have a rigid body and there are all the forces on that body are concurrent, what that means is that all the forces pass through a same point. So then we can treat that body as a particle. So we can just assume that it is just a single particle. So let's look at this example here. So we have this disc which has two hooks connected to it. So how many forces would be acting on this disc? First of all, there would be the force of gravity, and there would be a force due to this string, and there would be a force due to this string. Okay. But as we see that all these three forces, they are concurrent, which means that they all trace back to a single point. So now I can just assume that this whole body is not a body which has a definite volume. We can just assume that this is a particle. Okay. The reason for this would become more clear as we look at some more, we study next chapter, inshallah. Okay. So let's draw a few free body diagrams. So this is one of the examples from the book. So it says that the sphere in the figure shown has a mass of 6 kilograms and is supported as shown. We want to draw a free body diagram of the sphere and of the cord and the knot. So we want to draw 3 free body diagrams. So first of all, we would like to draw the free body diagram of the sphere. Okay. So what was the first step? First of all, we draw an outline of our object. So in this case, the outline is just a circle. So this is the outline. Okay. The next step was to draw all the forces acting on that sphere. So first of all, we know that there is going to be a force of gravity which is acting downwards. Okay. So we have a force of gravity. Okay. Next thing, we have a force which is because of this surface. There is a normal force pointing at 90 degrees from this surface. So we have a force acting like this. Okay. Another force acting like this. Okay. So because they are two forces, so let me just draw arrows. And the top force is because of this string which is connected to the top of the sphere. So we have another force here. So we have drawn all the 4 forces. This is the force due to gravity. This is the force due to normal force. This is the normal force from the left. This is the normal force from the right. And this is the tension in the string. Okay. So now we want to label all of these forces. So first of all, force of gravity, we already know that because the mass is 6 kilograms and we are assuming that g is equal to 10 meters per second squared. So we would just say that force of gravity is 60 newtons. Okay. And this force is an unknown force, so I would just call it Fc. This is the force towards point C, so I'll just call it Fc. And this is the normal force from the left, and this is the normal force from the right. So I can call this normal force Fn1 and this normal force as Fn2. Okay. Again, the names that I choose for the unknown forces is I have the liberty to change the name of the forces. So this is the free body diagram of the sphere. Notice that all of these forces, they are basically passing from the same point, which is the center of the sphere. So we can assume that this sphere acts just like a particle. Okay. Okay. So as you can see that we have drawn all the 3 forces. Again, the names are different. I have called it NA and they have called it NA and NB. I called it FNA, FN1 and FN2. Okay, this is the force due to gravity. Again, they are using the gravitational acceleration to be 9.8 meter per second squared, but we would always use the gravitational acceleration to be 10 meters per second squared. Okay. So let's move on. So next we want to draw the free body diagram of this cord. As you can see that this is just a cord which is just a piece of a string. The only forces are going to be two forces, one force from this knot and one of the force from this end, and these two forces are going to be equal because we are assuming that all the strings are ideal. So the free body diagram of the cord is very simple. We just draw two forces. One is the upward force due to the knot, and one is the downward force due to the sphere connected on this end. Okay. The next is the free body diagram of the knot. Again, we have three forces acting on the knot. One is the force in this direction, the other is the force along the spring, and the third is the force along the sphere, towards the sphere. Okay. So this is the free body diagram. We mention all three forces. All of these forces are unknown, so we just label all of these forces and draw them accordingly. So this is how we draw free body diagrams. Okay. So let's see if we have, how do we apply this condition of sum of all the forces is equal to 0 for a two-dimensional system. So we know that in a two-dimensional system, each force has two components, an x component and a y component, and sum of all the forces equals to 0 basically means that sum of all the forces in x equals to 0 and sum of all the forces in y equals to 0. Okay. So we look at this just example. We have this small sphere here which has total of 4 forces acting on it. So we would break down each of these forces into their components. So let me just say what that I mean. So I would write F1 just as equal to F1x I hat plus F1 y j hat. Again, this is a force vector. So and these are just scalars. Okay. Okay. Similarly, we would do the same for, we would do the same for F2 equals similar F3 and F4. So what is F1x? F1x is nothing but this length. This is F1x, and this is the F1y. Okay. So when we have broken all of these four forces into their x and y components, so this equation would simply translate to F1x plus F2x plus F3x plus F4x equals to 0. And we will write a similar equation for y, that sum of all the four y components of these forces is equal to 0. Okay. So I hope this is clear. Again, you would have done something similar in your FSE, but we want to reiterate these things and we want to do them in a more professional way.